Hello viewers, Wagadaro now taking you through the tutorial for A-Level Physics Paper 2, and this video will be on the marking guide of Physics Paper 2 for Uneb 2020. So where necessary, those constants would be used. So just start with question 1. Part A says, state the laws of refraction of light. So one we shall say that the incident ray, refracted ray, and the normal at the point of incidence all lie in the same plane. Then 2 we shall say that for a given pair of optical media, the ratio of sine of the angle of incidence to sine of the angle of refraction is a constant. So that's how the marks would be awarded for that part. So now we shall go to part B, Roman 1. So B Roman 1 says that deviation D by a prism of a small angle A and refractive index n is given by this. Use this to show that the focal length of a thin converging lens of refractive index n is given by that, where R1 and R2 are the radii of curvature of the lens surfaces. So just start by considering a ray parallel and close. Now this word is very vital in this derivation. We shall see why. So parallel and close to the principal axis incident on a lens at a small height h above the axis as shown below. So we need a ray diagram. So that is the converging lens. That is the ray parallel and close to the principal axis. So this is the principal axis, this is the length, and this is the ray parallel. Now that ray will be refracted to pass through the principal focus. And they told us the height h, a small height h above the axis, so this is the height h. And because it's the principal focus, this will be the focal length. Then this will be the deviation of this ray, because if this lens wasn't there, this ray would have continued in this path of the dotted line. But because of this, refraction occurs, and this will be the deviation of the ray. Then alternating angles, this angle will be equal to this angle. Now assuming D is a small angle expressed in radians, this deviation is a small angle expressed in radians, D will be approximately equal to tan D, and we know that tan D is equal to opposite over adjacent. So when with this angle here, opposite is h and adjacent is this, which is f. That is why here you see here h over f. But in the question you are told that D is equal to A in brackets n minus 1. So what I'm going to do, I'll come and substitute for this D to put there h over f, which is here. Then when I take this h this side, I'll come up with 1 over f equal to n minus 1, which is this, multiplied by a over h, because this h has gone here to become a over h, which is here. So let us call that equation 1. So you come and say that the normals at Q and R pass respectively through the centers of curvature C1 and C2 of the lens surfaces as shown below. So with that lens there, when you draw normals at this point and this point, they will pass through the centers of curvature. So let's do that. That is point Q, Then here there is point R. So I think we realize that this time there are no arrows, because if there is an arrow it implies it's a ray of light, but this time it is just normals. These are only normals, so be keen not to put any arrow on this line and also on this line. Now by geometry, A will be equal to alpha plus beta. We know that one exterior angle is equal to two opposite interior angles. Then assuming that alpha and beta are small angles expressed in radians, we shall get that alpha is approximately equal to tan alpha. I know that tan alpha is opposite over adjacent, so when I come here with this angle here, the opposite is h and the adjacent is from here up to here, which is the radius of curvature, R1. Similarly for tan beta, when this is beta, the opposite is h and the adjacent is this, which is the radius of curvature, which is R2. Now when I substitute here, A is here, alpha I'll put there this alpha, and beta I'll put there this beta here. Now with this you realize that h is common here, so I'll pull it out and take it this side to become A over h equal to 1 over R1 plus 1 over R2. So if you remember equation 1, in equation 1 we saw that 1 over f is equal to n minus 1 in brackets multiplied by A over h. So what I'm going to do, I will come here and substitute for A over h to come up with that expression, and basically that's the derivation they wanted. So that is how the marks would be awarded. Then on this slide, that is how the marks would be awarded. So now we shall go to part B, Roman 2. So part B, Roman 2 says the radii of curvature of the surface of a converging meniscus, know this word, converging meniscus, are 25 centimeters and 20 centimeters. Find its focal length if the refractive index of the lens is 1.5. So you already know that 1 over f is equal to n minus 1 in brackets 1 over R1 plus 1 over R2. So you're going to substitute for refractive index, then the radius, one radius will be negative, another one will be positive, because a converging meniscus is on this form. So one will be positive, another one will be negative. So when I simplify the whole of this using calculator, I'll come up with this. Therefore, get the reciprocal, f will be 200 centimeters. So that is how the marks would be awarded. So now we shall go to part C. Part C says describe an experiment to determine the refractive index of a liquid using a biconvex lens of known radius of curvature and a plane mirror. Know this word, known radius of curvature. That means that they have somehow eased the work for us. So let's start with a red diagram to help us ease the description. So that is a diagram to help us ease the description. I think realize that there's no need to show the ray, rays of light. Otherwise, if you were to show, they would have converged at this point. But because this is an experiment, it's not a ray diagram, so we don't need to show any ray because we're not going to derive anything. What we need is how the setup of the apparatus will look like. So this will be the object pin, and this is the image. I think this is dotted. This distance will be the focal length, convex lens, plane mirror. So let's look at the description. So just that a plane mirror is laid on a table with its reflecting surface upward, its reflecting face upwards, and a thin biconvex lens of known radius of curvature r. So we are given the radius is known, but you also have to define the radius. That's why we add it there. Known radius r is placed on it. So this is the plane mirror, the reflecting surface is upwards, and this is the convex lens on it. After which is that an optical pin O is clamped horizontally on a retort stand above the lens so that its tip, know that word, so that its tip lies along the principal axis. So this dotted line here represents the principal axis of this lens. So the tip must lie. I think realize that if you look at this, the tip is on the principal axis. Otherwise, we shall say that the pin is then moved up and down vertically while viewing from above, and a point is located where the pin coincides with its image eye, and there is no parallax between them. So this word parallax is needed, and this word coincides is needed. The distance f1 of the pin from the lens is measured and recorded. So before we go to the next slide, let's see the marks for this slide. So this one mark here, the word recovered means that it represents these two marks. So you can either give the mark here or you give it on this diagram. The lens is then removed from the plane mirror, and a small quantity, it should be a small quantity, of the test liquid is placed on the plane mirror. So the test liquid means that the liquid whose refractive index is needed. The lens is then placed back on top of the liquid, and the new position where the pin coincides with this image is located. So you repeat the procedure. The distance f of the pin from the lens is measured and recorded. So yeah, there was the word is. The focal length f2 of the liquid lens only is obtained from this expression. Remember now, this one was the combined focal length for both the liquid lens and the glass lens or the biconvex lens, and this f2 now is for the liquid lens only. So now the refractive index n of the test liquid is calculated from the expression that. So that is how marks would be awarded. So now we shall go to part D, Roman 1. So part D says that the focal length of a projector lens is 3.0 centimeters. If a magnification of 300 is required, find Roman 1 the distance of the screen from the lens, and Roman 2 the distance between the slide and the lens. So you know that m is equal to v over f minus 1. Therefore, come and substitute for the magnification and for the focal length. So we only have v as the only unknown. Therefore, When I make V the subject, V will be equal to this. And that is what they wanted in Roman 1. Then Roman 2, the distance between the slide and the lens. But remember, the screen is where the image is formed. Therefore, when the distance between the screen and the lens is the image distance, and the slide is where the object is. Therefore, the distance between the slide and the lens will be the object distance. So here comes that M is equal to V over U. Therefore, come and substitute for M, substitute for V, and make U the subject. So that is how marks would be awarded. And now shall go to question 2, part A, Roman 1, which says, state the laws of refraction of light. So here comes that one is that the angle of incidence is equal to the angle of refraction. Then 2 shows that the incident ray, reflected ray, and the normal at the point of incidence all lie in the same plane. So now shall go to part A, Roman 2. Roman 2 says, with the aid of a diagram, describe the operation of an optical lever in a Miller galvanometer. So here it is easier if we start with a diagram. So let's first draw a diagram for that. So that is a graduated scale. Then we have that fixed lamp. Then we have the mirror, which can be rotated. So when a ray from the lamp is incident normally on the mirror, then it is reflected back along the same path, and this point is noted. When a small current passes through the system which is connected to this mirror, the mirror will rotate to a position, say M2, and with an angle theta. That means that now this ray will be reflected in this direction to meet the graduated scale at this point, which is also noted. And from the laws, I think, remember, this angle here will be twice this angle. So the angle of rotation of the reflected ray is twice the angle of rotation of the mirror. I think you remember that. So how to measure these distances? Distance d and the distance here, which is x. So with that, we can go to our description. So you start by saying that a small plane mirror M1 is rigidly attached to a system which rotates when current flows through it, and a beam of light from a fixed lamp shines on the mirror as shown in the diagram. So this is the beam of light which shines on this mirror M1, and this mirror rotates when current flows through the system. So before I go to the next slide, those are the marks for this slide. So here comes that if light is incident normally means perpendicular on the mirror at A, the beam is reflected directly back along the same path, and a spot is obtained at O on the graduated scale placed just below the mirror. Think remember that. So this is the beam. Normally it is rotated back to meet the gravity scale at point O. So when a current I is passed through the system, the mirror rotates through an angle theta to position M2, and a spot of light is deflected through a distance x to position P on the scale. So this is what they mean, that this mirror will rotate to position M2, and now this incident beam will be reflected to position P, which is a deflection of x. The rotation of the reflected ray is twice the angle of rotation of the mirror. That implies that tan to theta will be equal to x over d. Now for small angles expressed in radians, tan to theta approximates to 2 theta. So tan of an angle approximates to that very angle. That implies that here now, where there is tan to theta, we should just put there 2 theta to be equal to x over d. Now since I is proportional to theta, the current flowing through the system can be determined, because now you have got theta. So that is how marks would be awarded. And now we shall go to part B. Part B says, describe an experiment to determine the focal length of a concave lens using a convex lens and a plane mirror. So first we shall put there a setup. So this is the source of light. This was the object screen with these cross wires acting as the object. This is the converging lens or convex lens. This is the diverging lens. And this is the image screen. Now I think realize that in the question they told us using a plane mirror, but here we are first putting there an object screen. So because that the procedure is that you first use an image screen, then after you'll be able to put there a plane mirror, as we shall see in the description. So let's start with the description. One shall say that the apparatus is arranged as shown. Now this statement helps you to link your content here with this setup, so don't forget it. So first, in absence of a concave lens, an illuminated object, in brackets wire goes O, is placed in front of a convex lens at a distance greater than the focal length. Now greater than the focal length helps you to form a real image. The position of the screen S2 is then adjusted until a clear image of the wire gauze is formed on it. Now here, I think you realize that you have not put the arrays because it's an experiment and it's not a derivation, so you don't need the rays. But if you have to put the rays at the point where when the image is sharp, it implies that it is at that point. So this is the point object, this will be the point image in absence of this lens. So that distance, when that happens, the distance from here to here is noted, or the position of S2 is noted. So that's the marks for this slide. So the new position of screen S2 is noted, and a plane mirror is now made to replace the screen. So here there was an N to replace the screen S2 at the same position. I think realize that now we are going to put there the plane mirror which was given in the question. So we are going to remove this image screen, and at that very point you put there the plane mirror. The concave lens whose focal length is required is now placed between the convex lens and the plane mirror. So now we shall place the concave lens between the plane mirror and the convex lens, which is here. The position of the concave lens is adjusted until a clear image of the wire gauze is formed on the object screen just besides the wire gauze. So if you look at this setup, when you replace this with a plane mirror, it implies that the when light is incident, normally, remember it will come like this, then like this. So here it will be incident normally, meaning that it is reflected back along the same path to form an image just besides the object of the wire gauze. So the distance between the concave lens and the plane mirror is measured and is equal to the focal length of the concave lens. So why is it so? If you look at this diagram, for the image to be found besides the object, implies that this ray from here went to this point, converged to this point, then it was diverged to meet this plane mirror. Remember, now when this lens is there, here there is a plane mirror, it's no longer an image screen, so it will meet at 90 degrees, meaning that this ray will be reflected back along the same path to go this side. So that means that because this one is parallel, it implies that it will this ray which is going back appears to come from the principal focus. Now that principal focus, remember, if this is the principal focus, it implies that the distance from here up to here will be the focal length. So that is why we said that the distance between this lens and the plane mirror is measured and is equal to the focal length. So now shall go to part C, Roman 1. So part C, Roman 1 says figure 1 shows a ray of monochromatic light incident on a triangular glass prism at an angle of incidence theta. Light just emerges from face AB of the prism. The speed of light in the prism is 2 exponent 8 meters per second. This is the diagram. So they said part 1, Roman 1, calculate the refractive index of the glass. So you know the speed of light in the prism, and we also know from the table of constants the speed of light in vacuum. Therefore, we shall come here and say that refractive index is equal to speed of light in vacuum over speed of light in the medium, which is glass prism now. So speed of light in vacuum is given in the constants, which is 3 exponent 8, and one here is 2 exponent 8 was given in the question. So in the end, we shall come up with 1.5 as the refractive index. So that is how marks would be awarded for this slide. So now we shall go to part C, Roman 2. Roman 2 says find the value of theta, which is the angle of incidence at surface AB. So here it's easier if we first redraw the diagram and put there some unknowns. So this ray emerges at 90 degrees, so it glazes the surface SC. So that means that taking Snell's law at surface SC, we shall come up with sine R2 equal to 1 over n, because this is now the critical angle, and critical angle is given by sine critical angle is equal to 1 over refractive index. So when I substitute, I'll be able to come up with the value of R2 as 41.81. But we know that this plus this is equal to this angle of the prism, which is 60. Therefore, substitute and be able to get the value of R1 as 18.19. Now, taking Snell's law at interface or surface AB, we shall come up with sine theta being equal to n sine R1. Therefore, substitute for n and R1 to come up with the value of theta as 27.92. So that was Roman 2. Now we shall go to Roman 3. Roman 3 says, explain what happens when the angle of incidence is greater. So here there was an E, is greater than theta. So that we shall come and say that the ray will emerge through surface SC when it is greater than theta. And the reason is that this is because the angle of incidence on this face SC will be less than the critical angle. So when it is less, there will be refraction. When it is greater than critical angle, there will be total internal reflection. But now, because it is less than the critical angle, there will be refraction. So it will emerge. So that is how marks will be awarded for this slide. So now shall go to part D. Part D says, describe adjustments of the telescope and the collimator of a spectrometer before making measurements. One shows that the eyepiece is adjusted until the cross wires appear clearly or are in sharp focus. Then from there we can now make adjustments on the telescope and show that the telescope is turned to face away from the collimator. And when that is done, the length of the telescope is adjusted to focus a distant object. Distant object helps you to get parallel light rays. So when that is done, the telescope is now turned to face the collimator directly. The slit of the collimator is then illuminated, and the length of the collimator is adjusted until the image of the slit is formed clearly on the cross wires. In this way, the spectrometer has been adjusted and ready for use. So here there was a Y missing to become ready. So that is how marks would be awarded for this slide. So now shall go to question 3. Question 3 part A says, state two differences between mechanical and electromagnetic waves. So one, we shall say that mechanical waves are generated due to mechanical vibration or oscillation of particles in the transmitting medium while electromagnetic waves are generated electronically or due to electron transition. Then 2 shows that mechanical waves propagate by oscillation of particles of the medium, while propagation of electromagnetic waves is due to varying electric and magnetic waves. Then 3 shows that mechanical waves require a material medium for propagation, while electromagnetic waves can travel in vacuum. And lastly, shows that mechanical waves propagate at relatively low speed or have a relatively long wavelength. So you can either talk about speed or wavelength, while electromagnetic waves propagate at relatively high speed or relatively short wavelength. So any of the two is okay. You can talk in terms of speed or in terms of wavelength. And that is how marks would be awarded. So now we shall go to part B. Part B says, describe an experiment to demonstrate that sound obeys the laws of reflection. So we need a diagram to help us is the description. So you come and say that a line is drawn on a sheet of paper, which is this. Then a normal N2, which is this, is drawn along the line AB. So this line was AB. And another line NS is drawn at a measured angle I, which is this line NS at a measured angle I. A hard cardboard is placed along AB. This is the hard cardboard placed along the line AB, and a hollow tube T1. This is a hollow tube T1 is placed along line NS, as you can see it there. So that is the mark for this slide. Other shall come as that a source of sound is placed at S. Another tube T2 is placed on the opposite side of N2 facing point N. So a microphone which is connected to the Y plates of a cathode ray oscilloscope is placed at the mouth of tube T2, and a vertical trace is observed on the screen. The position of the tube T2 together with the microphone is adjusted by moving them away from N2 until a maximum length of the vertical trace is observed on the screen. The position R is noted. I think you saw it in the diagram. Then the tubes are removed and a line RN is drawn. The angle RN2 is measured and is found to be equal to angle I. Now, since the angle of incidence is equal to the angle of reflection, it implies that sound obeys the laws of reflection of light. So basically that's how marks would be awarded. So now we shall go to part C, Roman 1. So Roman 1 says, explain what is meant by bits. So you come here and say that when two notes of equal amplitudes and nearly equal, so amplitudes is equal, but when it comes to frequency they should be nearly equal, are sounded together, they superpose. So that statement is very, very vital. So when they meet in phase, reinforcement takes place and a loud sound is heard. When they meet completely out of phase, cancellations take place and a soft sound or no sound is heard. A sound that rises and falls in intensity periodically is therefore heard and is called, that is what you call beats. And that is how marks would be awarded. So now we shall go to part C, Roman 2. Say that explain how beats are used to determine the frequency of a given note. So you come and say that test note is sounded together with a standard note, say a tuning fork. The number of loud sounds occurring per second FB are counted and recorded together with the frequency F1 of the tuning fork. The bit frequency is therefore given by the difference, which is F1 minus F2 or F2 minus F1. So F2 is the frequency of this test note which we are looking for. Now remember, these are two formulae, therefore we have to choose one and ignore the other. So to tell which is correct formula to use, one prong of the tuning fork is loaded with plasticine and the procedure is repeated and the bits per second counted, which will be now FB prime. After that we shall compare this FB prime with this FB here, which we got here. So if FB prime is greater than FB, it implies that FB is equal to F2 minus F1, implying that the test frequency F2 is equal to F1 plus FB. But if FB prime is less than FB, then FB will be got by F1 minus F2, implying that F2 will be equal to F1 minus FB. So in that way we shall have got the frequency of this test note using bits. So now we shall go to part D, Roman 1. So part D says that a car P moving at a speed of 108 km per hour towards a stationary observer and another observer in car Q moving in opposite direction with the same speed as P sounds a horn of frequency 256 Hz. Find the frequency of sound heard by Roman 1, the stationary observer, and Roman 2, the observer in car Q, where the frequency of sound in air is 340 meters per second. So let's start with Roman 1. So the first thing to do is convert this kilometers per hour to meters per second, which will give you 30 meters per second. Then you shall come and quote the formula, then you can substitute. So speed of sound in air, and this is this one for the source. This frequency was given also in the question. Therefore, now use the calculator, I'll come up with this as the required frequency. And that is how marks would be awarded. So now we shall go to part D, Roman 2. D Roman 2, they want the frequency of the observer in car Q. So here realize that they told us that the car P and car Q are moving in opposite directions, but they didn't tell us whether they are moving away from each other or towards each other. So that means that this question had two alternatives. Because you can be moving away from each other when you are in opposite directions, or moving towards each other when you are also in opposite directions. So we shall look at both cases. Let's look at the first one where both cars are moving towards each other. So the sketch would be as follows. So in this case, they're moving towards each other and in opposite directions. They're moving towards each other and in opposite direction. Therefore, the formula would be F prime is equal to V plus U naught over V plus US. And these velocities are the same, so that's why you see you have 30, 30. Then this V is that, and this V is this. This frequency was given, therefore when you use the calculator, you'll be able to come up with that as the frequency of the observer in car Q. But that is the case when they are moving towards each other. What about when they are moving away from each other? When that happens, the sketch will be in this form. Now we are doing these two alternatives because the question only said they are moving in opposite directions. The question did not specify whether they are moving towards each other or away from each other. Therefore, any of the two options is okay. So when you use this option of moving away from each other, the formula will be in that form. Therefore, substituting and use the calculator, we shall come up with this as the required frequency. So any of the two alternatives is okay. So now we shall go to part E. Part E says state two applications of Doppler effect. One is determination of the direction of motion of stars. Then 2 is estimation of the speed of stars. 3 is estimation of speed of cars using guns. And next is determination of plasma temperature. Then here we shall see that they are used in radar speed traps to determine the speed of a moving vehicle. So any two, that's how you could get the 1 mark. So now we shall go to question 4. Question 4 part A, Roman 1 part A says, what is meant by the following? Roman 1, ordinary light, and Roman 2, plane polarized light. So for Roman 1, we shall say that ordinary light is one whose electric vector varies or vibrates in every plane perpendicular to the direction of the light ray. Then Roman 2, we shall say that plane polarized light is one whose electric vector varies or vibrates in only one plane perpendicular to the direction of the light ray. So here it is in every plane, here it's only in one plane. Alternatively, we can say that this is one in which the variation of its electric vector takes place in only one plane, and also in the magnetic vector. So the key difference is this word: every plane, only one plane. So that is how the marks would be awarded. So now shall go to part B, Roman 1. So part B, Roman 1 says, describe how plane polarized light can be produced by reflection. So first we shall need a diagram. So these are two media, air and glass. Then this is unpolarized light incident on this boundary at an angle I to be reflected in that direction and also reflected in that direction, and here to be a Polaroid to help us view that light, and this will be the observer. So that diagram shall come and say that a narrow beam of unpolarized light is directed onto the medium, and the reflected light is viewed through the Polaroid. Starting with a small angle of incidence, the Polaroid is rotated about an axis through its plane. The angle of incidence is gradually increased, whereby at each angle of incidence the reflected light gets cut off from the observer as the Polaroid is rotated. At this point, the reflected light is completely plane polarized light. So that is how marks would be awarded. So now shall go to part B, Roman 2. Part B, Roman 2 says the refractive index of a Polaroid is 2.417. Find the polarizing angle of the Polaroid. Now this question was a little funny because we all know that a Polaroid does not refract light, yet in this case they used a Polaroid, so that means that it was not easy to do it. But if this word Polaroid was replaced with another word or another material which can reflect light, for example transparent glass, then the solution would be as follows. We would say that tan I is equal to n, therefore come and substitute for n to be able to get the angle of incidence as 67.52. But with this word Polaroid it will be hard because it can't refract light. So that was Roman 2. Now shall go to part C, Roman 1. Roman 1 says state Huygens principle. So you come and say that Huygens principle states that every point on a wave front may be regarded as a source of secondary spherical wavelets which move with the speed of the wave, and the new wave front is the envelope which touches the surfaces of the wavelets. And that is how marks would be awarded. So here we wouldn't award because of this word Polaroid. So now we shall go to part C, Roman 2. So Roman 2 says use Huygens construction to verify the laws of reflection of light. So we shall come here and say that consider a parallel beam of monochromatic light incident on a plane reflecting surface xy such that its direction of travel makes an angle I with the normal to the surface as shown. So we need a diagram. There is xy, then we have a parallel beam which is reflected. So you come and say that if 2 points A and B on the same wave front travel to points C and D respectively. So respectively in time t, then so A, that means that A travels to point D and C travels to point C. That's what the word respectively means. In the same time, it implies that this distance AD is equal to BC because they have used the same time and the speed is the same. And the angle BAD is 90 degrees, and also this one is 90 degrees. So that the marks for this slide. So you can see that in triangle ABD and BCD, BD is common to both. Therefore, the two triangles are congruent. That implies that this angle CBD is equal to angle BCA. And this angle is 90 minus R, or this angle is 90 minus I. Therefore, I will be equal to R. Therefore, the angle of incidence I is equal to the angle of reflection R. So basically, that's what they wanted. So now we shall go to part D, Roman 1. So D Roman 1 says, what is a diffraction grating? So you can see that a diffraction grating is a sheet of glass or polished metal with large number of close, parallel, equidistant lines ruled on it using a diamond pencil. So that's how marks on this slide would be awarded. So now shall go to part D, Roman 2. D Roman 2 says, describe an experiment to determine the wavelength of monochromatic light using a diffraction grating and a spectrometer. So we shall need a diagram, that is monochromatic source of light. Then we have here a collimator, then circular table with screws, diffraction grating. So this will be light from this source incident on this diffraction grating, diffracted in that direction, and is viewed using telescope T1. Then in this direction also, this other diffraction will be viewed using telescope will be put at position T2. And that angle is called theta. So you have start our description and say that the telescope is adjusted to focus parallel light. Remember, we first make an initial adjustments before we go to the real experiment. So this was the adjustment of the telescope. What about for the collimator? The collimator is adjusted to focus parallel light and the table is leveled. The telescope is turned to receive light directly from the collimator. The grating is placed on the table so that its plane is perpendicular to the incident light from the collimator. So that's how marks for this slide would be awarded. So the zero order image is now received at the telescope when it faces the collimator directly, and the position T is noted on the scale. So keeping the turntable fixed, the telescope is rotated to one side until the first order image is obtained. The new position T1 of the telescope is noted. The telescope is restored to position T and again rotated in the opposite direction until the first order image is again obtained. The new position T2 of the telescope is noted. The angle theta between T1 and T2 is measured and recorded. The wavelength lambda is now calculated from lambda is equal to d sine theta over 2, where d is the spacing of the grating stroke lines. So that is how marks would be awarded. So now we shall go to question 5. Question 5 part A says define the following as applied to Earth magnetic field. Roman 1, magnetic meridian, and Roman 2, angle of dip at allocation. So one, we shall say that the magnetic meridian is the vertical plane in which a freely pivoted magnet sets itself. Then for Roman 2, we shall say that the angle of dip is the angle between the resultant Earth's field intensity and the horizontal. And that is how marks would be awarded. So now we shall go to part B. So part B says determine an experiment to compare the magnetic flux density at the center of a coil carrying current with a horizontal component of the Earth's magnetic flux density. So we need a diagram to help us is the description. So that is a circular coil. Magnetometer. These are connecting wires. So that is a circuit, and this is what we call the reverse switch. So we shall now come and say that a circular coil is set with its plane in the magnetic meridian of the Earth. Then we shall come and say that the deflection magnetometer is mounted on a vertical axis at the center of the circular coil with its pointer initially at the 0 max. So this is the magnetometer mounted on the circular coil. But remember, the circular coil has to be in the magnetic meridian for this magnetometer to read 0 max. The coil is then connected through a reversing switch to a battery rheostat and the ammeter as shown. So this is the rheostat, this is the ammeter, this is the battery, and this is the reverse switch, and these are the connecting wires. The rheostat is adjusted so that the ammeter reads a suitable value of current I. So that's how marks for this slide would be awarded. So now we shall come and say that the deflections theta 1 and theta 2 at both ends of the pointer are read and recorded. The current in the coil is reversed, and the new deflections theta 3 and theta 4 are read and recorded. The average deflection theta is calculated from the formula that theta is equal to that. So these are the 4. Therefore, to get the average, you have to divide by 4. So if BH is the horizontal component of the Earth's magnetic flux density and BC is the magnetic flux density of the coil due to the current, it implies that BC over BH is equal to tan theta. So that can be illustrated in this way. So that is our theta, this is BH and this is BC. Therefore, this will be BH, BC and BR. Therefore, this is theta, implying that theta is equal to opposite over adjacent. I mean tan. Therefore, that's where tan theta equal to BC over BH is coming from. So that is how the 5 marks would be awarded. So now we shall go to part C, Roman 1. So C Roman 1 says a rectangular coil of a wire of n turns and area capital A is suspended at the midpoint of one side by a fiber of torsional constant K. The plane of the coil is initially set parallel to the horizontal uniform magnetic field of flux density B. Roman 1. Derive an expression for the angle of rotation of the coil when a current I flows through it. So shall need an illustration. So that will be the coil with dimensions L and B. And that is the field. And this is the current. So you come and say that when current flows in the coil, the force on PQ and RS is 0. So force on this side, PQ and RS will be equal to 0. By Fleming's left-hand rule, on sides PS and QR, the force on side PS will be equal to NBIL and to be outwards. So here it will be outwards. The force on QR will be NBIL and it will be inwards. So these two forces constitute a couple which rotates the coil until it is stopped by the hair springs. So on this slide, those are the marks. So you come and say that if theta is the angle of rotation, it implies that torque on the coil is equal to force times the perpendicular distance between them. The force is this, and the perpendicular distance will be B cos theta. You resolve. So when I rearrange, remember L times B gives you the area of that coil, which is A. So where A is equal to the area of the coil PQRS. Therefore, in equilibrium, the torque set by the hairspring will be given by K theta. That implies that this will be equal to this in equilibrium. So that is how the 4 marks would be awarded. Now we shall go to part C, Roman 2. So Roman 2 says, state the modification that would be required to return the arrangement in C Roman 1 into a moving coil galvanometer. So 1 is that the magnetic field should be made radial. 2 is that the coil should be supported by jeweled bearings. 3 is that the coil should be wound on a light conducting frame. Then 4, the frame on which the coil is wound should turn about a soft iron cylinder. And 5 is that a pointer which can move along a linear scale should be attached to the coil. So any 4, you get yourself the 2 marks. So now we shall go to part D, Roman 1. So part D, it says that figure 2 shows 2 parallel conductors A and B, each carrying current of 2 ampere into the plane of the page. And this is the diagram. Roman 1, find the resultant magnetic flux density at C. And Roman 2, draw the magnetic field pattern due to currents through A and B. So let's start with Roman 1. They want the resultant magnetic flux density at C. So we need to redraw the diagram so that we can show the directions of the flux density. So that's what was given. So this will be flux density due to this, then flux density due to B. Therefore, these are 2 directions, so you can use parallelogram by completing the rectangle, since this is 90 degrees. So this is the same as this, and this is the same as this. But remember, this is dotted and this is dotted. You must be keen with that. Therefore, when I join from here to here, that will be the resultant which is required. So this is our resultant, and this is the direction to line CB. So with that sketch, we can now go ahead to answer our questions, but we need to get some of the angles. This angle theta, the good thing, this is a right angled triangle, therefore sine theta is equal to opposite over hypotenuse. So this angle here, the opposite will be this, which is 0.3, and here over hypotenuse, which is this, which is 0.5. That implies that theta 1 is equal to 36.87. Then angles of a triangle add up to 180, therefore theta 2 will be equal to 90 minus theta 1, since this is already 90, to give you 53.13. So for this slide, that's how marks can be awarded. So now we need to code the formula for magnetic flux density, which is that. Therefore, for BA, we shall substitute this one is a constant and it's known, 4 pi exponent -7. Then current was 2, it was given the question. This 2 pi is maintained since it's there on the calculator, and the radius is the distance, which is 0.4 meters. When I use a calculator, I'll come up with this, so it is advisable to leave your answer in scientific form to avoid the too many 000 something. Then you shall also get BB, so you'll substitute constant, current, 2 pi, and the distance, which is 0.3. So in that case, I'll come up with 1.3333 exponent negative 6 Tesla. So the resultant, since it was a right angle triangle, I'll just use Pythagoras theory, which gives me square root of this plus this, and in the end I'll come up with this as the resultant. But we also need the direction, so direction tan alpha will be equal to this, implying that alpha is 53.13. Therefore, we shall conclude that the resultant magnetic flux density at C is this, which is here, in the direction this with side CB. So that is how marks would be awarded. Now we shall go to part D, Roman 2. Roman 2, they said draw the magnetic field pattern due to currents through A and B. So if X is the neutral point, then you can now go ahead and draw, and we locate X as the neutral point. I think realize that this side, the spacing is smaller than this side, and here the spacing is large. You must be keen as you are drawing it. Here the spacing is wider, here the spacing is smaller, this side. That is one. Then two, you realize that here the curvature keeps on reducing. Here it was more curved, less curved, almost linear. So you must be keen with that. Then this X is what we call the neutral point. But you must be keen, here the spacing is closer, and also here it's closer, here it is wider, here it is wider, and here the curvature keeps on reducing. So that is how marks would be awarded. So now we shall go to question 6. Part A, Roman 1 says, define self-induction. So self-induction is the generation of EMF in the coil due to changing current in the same coil. Then we shall go to part A, Roman 2. So Roman 2 says, derive the expression this, where L is the self-inductance of a coil and I is the value of the alternating current flowing in the coil. So one, we shall say the magnetic flux is given by this symbol, linking the coil is given by this, phi equal to AB, area times flux density. But we know that B is proportional to current, implying that flux is also proportional to current given this, because area will be constant. Therefore, if this B is proportional to current, even this one will be proportional to current. Therefore, when I put a constant of proportionality, it will be capital L. So if the current in the coil changes, then the flux linkage also changes. So what does that imply? It implies that the phi dt is equal to the Li dt. Remember this one, when this one changes, even this one will also change. But remember this one is this L is a constant, so it can be pulled out to come up with L di dt. So know that in this EMF is given by negative of d phi dt. So I'll come and substitute for d phi dt to come up with E equal to negative L di dt, which is required. So that is how marks for this slide would be awarded. So now we shall go to part B, Roman 1. Part B, Roman 1 says, figure 3 shows two coils A and B coil B is connected to an ammeter A2, while coil A is connected to an alternating voltage source and an ammeter A1, as shown in this diagram. Roman 1. Explain why current flowing through A1 in circuit A is less than the current that would flow through a straight wire of equal resistance when connected across the same voltage. So you come that when a straight wire of resistance R is connected across a voltage source V, back EMF in the wire is negligible, implying that the current which flows through the coil is I1 equal to V over R. So let's call it I1 and it will be given by V over R. Now that is for a straight wire. What about for a coil? When a coil of the same resistance R is connected across the same voltage V, back EMF is induced in it, and this reduces the current flowing through the coil into a value of I2, which is given by V minus EB over R. Remember, back EMF is in the direction opposite, therefore the voltage will reduce to become V minus EB, and therefore the current will be V minus EB over R. We shall therefore conclude that since I2 is less than I1, it implies that current in A is less than that in the straight wire. So that is how marks would be awarded. So now we shall go to part B, Roman 2. Roman 2 says explain what would be observed on the ammeters when the coils are brought closer to each other. So you come and say that when the distance between A and B is reduced, the magnetic flux linking coil B due to the changing current in A increases. The induced EMF and hence the induced current in the circuit therefore increases. Accordingly, the reading of A2 will increase because of the increase in current. The induced current in B produces a changing flux in B. This flux opposes, note this word, opposes the flux produced by the applied voltage in A, and so reduces the total flux linking coil A. Back EMF induced in coil A reduces, and the resultant voltage in the circuit increases. That implies that the current through A increases, hence increase in the reading of A1. So that is how marks would be awarded. Now we shall go to part C, Roman 1. So C Roman 1 says a motor consists of a rectangular coil of area 20 centimeters squared having 50 turns. A current of 2.5 ampere is passed through the coil. Roman 1. Calculate the flux density of the field in which the coil is placed if the torque of 0.30 Newton meter acts on the coil. So you come and say that for a motor, the field is radial. I believe you know that. Therefore, torque will be equal to BA, BA, flux density, area, number of turns, and current. So shall substitute. This was given in the question. Then B is unknown. Area is that. Now the area was given as 20 centimeters squared, but you have to convert it to meters squared by multiplying it by 10 to the power negative 4. Number of turns 50, current is 2.5 ampere. So in that case, B is the only unknown. Therefore, when I make it the subject, B will be equal to 0.1 Tesla. So that was Roman 1. What about Roman 2? Roman 2 says calculate the back EMF in the coil if the coil is rotating at 2400 revolutions per minute. Note that's per minute. So you come and say that for a motor the field is radial, already know that. Therefore back EMF is equal to NAB omega. This omega in terms of frequency it will be 2 pi f. Therefore you come and substitute number of turns 50, area is 20 multiplied by 10 to the power negative 4 to become meters squared. So let's use this one. So this N is number of turns, area, this B is what we have got here, then this 2 pi is here, then the frequency is this. Because it was per minute, we have to change it to per second. That's why we divide by 60. So when I use a calculator, the volt back EMF will be 30.1593 volts. So that is how marks would be awarded. So now we shall go to part D, Roman 1. The Roman 1 says, explain how eddy currents are produced in a motor. So you come as that as the coil of the motor rotates in the magnetic field, the core onto which the coil is wound rotates in the magnetic field of the motor. The changing flux linking the core induces EMF in the core. This EMF causes current to circulate in the core in such a direction to oppose the rotation of the core. These are eddy currents. So now we shall go to Roman 2. Roman 2 says, how are effects of eddy currents minimized in a motor? So the effect of eddy currents are minimized by laminating the core of the motor. So that is how the marks would be awarded. So this should be 1, not 3. So now we shall go to question 7. Question 7 part A says, define the root mean square value of an alternating current. So you come and say the root mean square value of an alternating current is the value of steady current that dissipates heat in a given resistor or given resistance at the same rate as, know that word, as the alternating current. And that's how marks will be awarded. So now we shall go to part B. Part B says, with the aid of a diagram, describe the structure and action of a moving ion meter. So in this case, they didn't specify whether it is repulsion type or attraction type. So we are going to, in this video, we are going to do both approaches. So whether you do repulsion type or attraction type, any is okay. So let's start with the repulsion type. We shall need a diagram. So you also need to do some labeling. So this is the non-linear scale. That is why here the spacing is varying. That is the pointer. This is the solenoid, hairspring, pivot, fixed soft iron rod, and movable soft iron rod. And these are the terminals. So that is how marks will be awarded for this slide. So Jakama says that current to be measured is passed through the coil via terminals T1 and T2, creating a magnetic field at the center of the coil. Whatever the direction of the current, the two soft iron rods get magnetized in the same sense. That means temporality, and so they repel one another. The movable iron rod is pushed away, and as it moves, the pointer rotates over the scale until it is stopped by the restoring torque of the hairspring. At this point, the deflection torque is proportional to the force of repulsion, which is also proportional to the square of current. Therefore, the deflection theta is proportional to this mean square of the current. And in that case, this would be alternating current would be measured. So that is how marks would be awarded. But there is also an attraction type. So we need a diagram. Let's first draw a diagram. So you also need some labeling. So it's the nonlinear scale, hair dash spot, this is the pointer, hairspring, pivot, soft iron block, and solenoid. So that is how marks would be awarded for this slide. So Jakama says that current to be measured is passed through the coil via terminals T1 and T2, creating a magnetic field inside the coil. Whatever the direction of current, the coil magnetizes and attracts the soft iron block. As the block turns, the pointer rotates over the scale until it is stopped by the restoring torque of the hairspring of the hair dash. So at this point, the deflection torque is proportional to the force of attraction, which is proportional to the square of the current, i.e. deflection. This is proportional to that. So that is how marks will be awarded for this attraction type. So now we shall go to part C, Roman 1. So part C says a 8.0 microfarad capacitor is placed across a 200 volt RMS supply. RMS means root mean square. Roman 1 says calculate the amplitude of the current which flows if the frequency of the SC is 50 Hz. So we have the capacitance, we have the voltage or the PD, and we have the frequency, and they want the amplitude of the current, or in other words maximum current. So you know that root mean square value of the current is given by 2 pi f c v RMS. So if this is RMS, this will also be RMS. Now we can't put here I max. It's true they want maximum value, but we can't get it because the voltage we are given, or the PD, was in RMS. So you have to first get the I RMS, then after that we shall be able to get the maximum current which they want. So I RMS is equal to 2 pi f CV. So I shall substitute this 2 pi. Pi is this. Frequency was given as 50 Hz. Capacitance was microfarad, so you change it to farad, which will be 8 times 10 to the power negative 6. Then the voltage was given as 200. So when I use the calculator, the whole of this will give me 0.5024 ampere. So now that I've got IRMS, I can be able to get my I naught, which is the maximum current which they want. So maximum current will be IRMS multiplied by root 2. So this one here multiplied by root 2 will give you this, which is 0.7105 ampere, and that is what they wanted. So now we shall go to part C, Roman 2. Roman 2 says explain what happens to the value of the current in the circuit if the frequency of the SC is increased. So you come and say that if the frequency of the alternating current is increased, here increased, the D was missing, the number of times the capacitor charges and discharges in a unit time also increases. That means that the quantity of charge flowing in the circuit in a unit time increases also, and therefore current increases. So increasing the frequency increases the current. Alternatively, we can now use various formulae to come up with the outcome. So we know that reactance or capacitive reactance is equal to 1 over 2 pi fc. That implies that capacitive reactance xc is proportional to 1 over f, because 2 pi c are constant. Therefore this will be proportional to 1 over f. But this, I think you see, it is 1 over f, meaning that X capacitive reactance is inversely proportional to F. Now inversely proportional means that when one increases, the other reduces. Therefore, in the question we are told that frequency is the one which is increases. Therefore, we shall come and say that if frequency increases, capacitive reactance will reduce. So now that we know the capacitive reactance has reduced, we shall come and say that we know that I is equal to V over capacitive reactance. Therefore, when this is constant, it implies that I is proportional to 1 over capacitive reactance. So this 1 over this implies that I is inversely proportional to capacitive reactance. So what does that mean? You have already seen here that capacitive reactance reduces, implying that current will increase. So you can either write this or this, and of the two is okay. And that is how the marks would be awarded. So now shall go to part D. So part D says, explain the phase relationship between the applied alternating voltage across an inductor and the current that flows. So you come and say that when alternating current flows in the coil, back EMF, which are denoted by EB, is induced in it. So this is induced, not induces, is induced in it. But we know that EB is equal to negative L di dt. So this is the inductance and this is the I dt, current, rate of change in current. Now for a pure inductor, this voltage is equal to negative of the back EMF. Therefore, from here we shall come and say that V is equal to positive L di dt. So when current is 0, the rate of change of current di dt will be maximum, implying that V is maximum. And when current I increases to a maximum, the rate of change of current I dt is equal to 0, implying that V is also 0. So therefore V and I are out of phase by 90 degrees. So that is how marks would be awarded. So now I shall go to part E. So part E says a sinusoidal alternating voltage V equal to V naught sine omega t is applied across a resistor of resistance R. Derive an expression for the mean power dissipated in the resistor. So we are given that V is equal to V naught sine omega t. That implies that the instantaneous power, we know that instantaneous power is equal to V squared over R, so instantaneous power is equal to V squared over R. But we know that V is this, therefore V squared will be the whole of this squared over R. Then when I open this bracket, this square affects this and this, so this will be V naught squared and this will be sine squared omega t. But we wanted mean power, therefore we shall come and say that average power. So these symbols are there to imply average power. So average power this, so when I put this symbol here to imply that, I'll also put that symbol here to mean average voltage squared. But this is a constant, so it can come out to become v naught squared over r, in brackets we put sine squared omega t. But we already know that the mean value of sine squared omega t is equal to a half. So this can be derived, but in this case they don't want you to derive it. You have to just quote it. That is equal to a half. Therefore, you shall come and substitute to come up with average power being equal to v naught squared over 2r. And that is how marks would be awarded. So now we shall go to part F. Part F says find the amplitude of the SC which dissipates energy in a resistor equal to 3 times that produced by a DC of 2 ampere passed through the resistor under the same conditions. So energy due to AC is equal to 3 times energy due to DC. That's what we are given in the question. So you come and substitute. Energy due to AC is given by that. Energy due to DC is given by that. So when I simplify, RT can cancel, and this half can go this side to become 6. When I put square from both sides, I come up with I naught being equal to IDC multiplied by root 6. So we are given this current is 2, so it will be 2 times root 6 to give you 4.8990 ampere. And basically that's how marks would be awarded. So now we shall go to question 8. Part A says what is meant by potential difference? So Jakamas, that potential difference is the work done to transfer stroke move a positive charge of 1 coulomb from one point to another in an electrical circuit. So it's the last condition. Most students forget it, but it has to be included. And that is how you could get your 1 mark. So now we shall go to part B, Roman 1. B Roman 1 says describe an experiment to verify Ohm's law. So we shall need the circuit diagram. Let's first draw a circuit diagram. Okay. So you come as the apparatus is set up as shown above. So this is the diagram or the setup. So before anything, you have to remember to first close this switch K, because when it is not closed, the diagram does not work. So that's why you start with switch K is closed and the rheostat P adjusted, so that the ammeter and the voltmeter read suitable values of I and V respectively. The ammeter and voltmeter readings are recorded. The procedure is repeated for different values of current I by adjusting the rheostat P, and the corresponding PDV is read from the voltmeter. The results are tabulated and a graph of I against V is plotted. A straight line graph through the origin is obtained, implying that I is proportional to V, and hence this verifies Ohm's law. And that's how marks would be awarded. So now we shall go to part B, Roman 2. So Roman 2 says a 12-volt battery is connected across a potential divider of resistance 600 ohm. If a bulb with filament resistance of 100 ohm is connected across 1/3 of the potential divider, know that word, 1/3 of the potential divider, determine the amount of electrical energy consumed by the bulb in 10 seconds. So let's first draw a sketch of what has been given in the question. So that is it. So we shall come and say that, remember, they told us that this one is 1/3 of the whole of this. That is why you see here Rxy is equal to 1/3 of Rxz of the whole of this. And the whole of this was given as 600 ohm in the question. That's why you see here 600 ohm. So when I multiply, I come up with 200 ohm as the resistance from X to Y. Since these two are in series, it implies that the remainder or the resistance of YZ will be 600 minus 200 to give you 400 ohm. Now these two resistances are in parallel, so combining those two resistances in parallel, we shall come up with product over sum. So it's the product in the numerator, sum in the denominator, to come up with 66.67 ohms. Then PD across XY, we can also use the potential divider rule, that PD across XY is equal to this resistance, combined resistance, over the total, which is this, multiplied by the total PD, which is that. So that is how the potential divider rule is applied. So when I substitute, R1 is that, R1 is here, RAYZ is there, total voltage is there. So when I use a calculator, I'll come up with 1.7144 volts. Therefore, the energy consumed by the bulb is equal to power times time. So this is power and this is the time. So the power is Vxy squared. Remember, it should be V squared over R. So, and R is here. And the time was given as 10 seconds. So when I use the calculator here, I'll come up with 0.2939 joules. And that's how the marks would be awarded. So now shall go to part C. Part C says, describe the mechanism of heat generation in a current carrying conductor. Shall come and say that when current flows through a conductor, conduction electrons gain kinetic energy and drift through the metal. As they move, they collide with the atoms of the metal and their lattice positions, losing some of their kinetic energy to the atoms. The atoms therefore vibrate about their mean positions with large amplitude, which manifests as increase in temperature. You can either use the word increase in temperature or you say increase in internal energy of the atoms. And that is how marks would be awarded. So now shall go to part D. So part D says, describe an experiment to determine internal resistance of a cell using a potentiometer. So we shall need a circuit diagram. Let's first draw a circuit diagram. So you come that the setup is as shown. So like I told you, such experiments you must be keen with the switch. So the switch is with the switch at position 1, so the switch is placed in contact with position 1 here, meaning that this circuit is complete and this one is incomplete. Therefore, with the switch at position 1, the jockey is tapped at different positions along the wire AB until a point is found where the galvanometer shows no deflection. The balance length L0 is noted. Switch K is then connected to position 2 and the rheostat adjusted to a suitable value. The new balance point is located and the new balance length L is noted. So that's how marks for this slide would be awarded. So we shall continue and say that the procedure is repeated for different values of R, and the results are tabulated including values of 1 over L and 1 over R. A graph of 1 over L against 1 over R is plotted and its slope S is determined. The internal resistance R is then small r is then calculated from small r equal to S L naught. And that is how marks would be awarded. So now we shall go to question 9. Part A says define the following: Roman 1 electric field intensity and Roman 2 electric potential. For Roman 1, we shall say that the electric field intensity is the force experienced by a positive charge of one coulomb placed at a point in the electric field. Then for Roman 2, we shall say that the electric potential is the work done to move a positive charge of one coulomb from infinity to a point against the electrostatic field. So that was Roman part A. What about part B? Part B says sketch two graphs on the same axis to show the variation of electric field intensity and electric potential with distance from an isolated point charge. Remember, they have said point charge. Point charge. So what does that mean? So that the axis here, the vertical, we shall put VOE because we are going to draw two graphs on the same axis. That is one for V, and the one for E is that. So as you draw, you must remember that V is above E. That is 1, and 2 is that there is no sphere because they said point charge. Most students are fond of drawing a sphere here, then they can draw that graph for E. That will not be okay because they said point charge. So now we shall go to part C. Part C says describe an experiment to show that the potential over the surface of a pear-shaped charged conductor is constant. So we shall need a diagram. Let's first draw a diagram to help us is the description. So that is a pear-shaped conductor which is charged, and this is the insulating stand so that it can retain this charge. This is the conducting wire, and this is an insulating rod. That is the cap of the gold leaf electroscope, and this is the leaf of the electroscope, and this is the insulator. I think you realize that this electroscope is not earthed. Make sure that you don't earth this electroscope. If you earth it, then the experiment cannot work. So shall come out that a wire wound on an insulating rod is connected to the cap of a neutral gold leaf electroscope. This is a wire wound and connected to this cap. The free end A of the wire is connected to the surface of the charged conductor. So this free end is connected to the surface. So that is one wire. Then another wire is connected to point B on the conductor, which is here, and to point C on the electroscope. And when you do that, the leaf will be seen to collapse. So that's how marks will be awarded for this slide. Like I told you, earthing must not be done. Then we shall come and say that the leaf remains collapsed as the free end A of the wire is tapped at different points on the conductor. So this implies that the PD between any 2 points on a conductor is 0, and thus the potential is constant at all points on the surface. So this was a repetition, you can remove it. And so that was part C. Now we shall go to part D. So part D says figure 4 shows two parallel metal plates placed 10 millimeters apart in a vacuum with a potential difference of 100 volt between them. A point charge of positive 2 microcoulomb is transferred from A to C following the path shown from A to C. So from here to here, then from here to here. If AB is parallel to the metal plates and BC is 10 millimeters long, find the work done in moving the point charge from Roman 1 A to B and explain your answer. Then Roman 2 from B to C. So you come as that electric potential at A given by denoted by VA is equal to 5 over 10 multiplied by 100, which gives you 50 volts. So where does that come about? So when you go back to this question, we know that from here to here is 10 millimeters and the PD is 100, from 0 to 100 volts. Therefore 10 millimeters corresponds to 100 volts. What about 5 millimeters? 5 millimeters will be half of 10, meaning that it will represent half of this 100 volts. That's why you saw 5 over 10 multiplied by 100 to get the volts for 5 millimeters, and that will be VA because this is point A. So similarly, electric potential at B is also equal to 5 over 10 multiplied by 100, which is 50 volts, since the distance is also the same, 5 millimeters. Therefore, work done in moving the charge from A to B is given by WAB, which is Q multiplied by VAB. Then Q is this 2 microcoulomb, but it has to be converted to coulomb. That's why you see up times 10 to the power negative 6. Then VAB is the difference, potential difference. So the difference between these two is 0. 50 minus 50 is 0. So 0 times this will give you 0 as the work done. They also told us to give a reason, such as that there is no change in electric potential from A to B. So that is how marks would be awarded for this slide. So now we shall go to part D, Roman 2. Roman 2 says, find the work done in moving the point charge from B to C. So from B up to C. Now here we also need to resolve for we need to do some resolving so that we can get this distance from here to here. So from here to here I have to resolve the whole of this horizontally to give me 10 cos 60. Now 10 cos 60 plus this will be the total distance from here up to here. So let's see how that one is done. So electric potential at C is equal to that distance, like I told you, 5 plus 10 cos 60 over 10, which is the total multiplied by 100. So these two, when you add the two, you come up with 10. So 10 over 10 is 1. That is why you see here 100 volts for VC. Therefore, work done in moving the charge from B to C will be equal to WBC, which is 2 times VBC. So the charge is 2 microcoulombs, so you change it to coulombs. Then VBC is the difference, potential difference, which will be 100 minus 50, which is here. Now when I multiply these two, I'll come up with 1 exponent negative 4 joules. So now we shall go to part E, Roman 1. So part E says, an alpha particle of charge positive 3.2 exponent negative 19 coulomb and mass 6.8 exponent negative 27 kilograms travels with a velocity v directly towards a nitrogen nucleus which has a charge of positive 11.2 exponent negative 19 coulomb. The alpha particle reverses direction at a distance of 9.4 exponent negative 15 meters from the nitrogen nucleus. Roman 1. Explain why the alpha particle reverses direction. So you come and say that the alpha particle loses kinetic energy as it approaches the nitrogen nucleons, and this is transferred to electrostatic potential energy in the field. At some point, all the kinetic energy of the alpha particle is lost and it is repelled back by nitrogen nucleons. And that is how marks would be awarded. So now shall go to part E, Roman 2. Roman 2 says, find the initial velocity v of the alpha particle. So we need to know that the initial kinetic energy of the alpha particle in joules is equal to potential energy of the nucleus alpha particle system at a distance of closest approach. So this kinetic energy is given by this, and this one given by this. So when I substitute, half is here, mass is there, V is what they want, K we know it as that, Q1 is that, Q2 is that. You convert to, it was already converted. Then R is that, it was already in meters. Now when I make V the subject, I'll come up with the value of V being equal to 1.0046 exponent 7 meters per second. And that is how marks would be awarded. So now shall go to question 10, part A, Roman 1, which says define capacitance of a capacitor. So you come as that the capacitance of a capacitor is the magnitude of charge required to cause a change of 1 volt in the PD across the plates of the capacitor. Alternatively, we can say that this is the ratio of the magnitude of charge on either plates of the capacitor to the potential difference across its plates. So that was Roman 1. What about Roman 2? So Roman 2 says a conducting sphere of radius 7.5 centimeters is maintained at an electric potential of 9 kilovolts. Calculate the charge on the sphere. So now that V is equal to K Q over R. That will come and substitute for V. It was kilovolts, so change to volts, but that's why I multiply by 10 to power 3. K we already know it, Q is what we don't know it, and R we know it. So it was in centimeters, we convert to meters. Then when I make sure the subject Q will be equal to 7.5 exponent negative 8 coulombs. And that is how marks would be awarded. So now shall go to part B. So part B says describe an experiment to determine the effect of the separation of the plates on capacitance of a capacitor. So we shall need a diagram. Let's first draw a diagram to ease the description. So in this case, the gold leaf electroscope must be earthed. So it should be keen when to earth and when not to earth. So two metal plates X and Y are set close to each other but not touching as shown above. So in this statement we have already defined what X and Y are. So plate Y is given a charge of Q and the divergence of the leaf of the electroscope noted. Plate X is slowly removed away from plate Y and the divergence of the leaf is seen to increase. This means that PD, V between the plates has increased. Now from C is equal to Q over V, it implies that capacitance has reduced because C will be inversely proportional to V. When V increases, capacitance has to reduce. Because this one has reduced, when you increase the separation, it implies that the separation and capacitance are inversely proportional. That is why you see here C is inversely proportional to D, where D is the separation of the plates. And that is how marks would be awarded. So now shall go to part C. So part C says that the plates of a parallel plate capacitor are separated by a distance of 2 mm in air. If the surface area of each plate is 5.0 cm squared and a PD of 6 volt is applied across the plates, find the magnitude of the charge on each plate. So charge will be equal to electric field intensity multiplied by the area, cross-section area multiplied by area of the plates and multiplied by the permittivity of free space. And we know that this electric field intensity is equal to V over D, where V is the PD and D is the separation area of the plate, then permittivity of free space. So this one is a constant, it is here, and this is the PD, which is that, and this is the area. You convert to meters squared, and the separation you also convert. So when I use the calculator here, I'll come up with this. So it is advisable to use scientific form because these will be very many zeros. So now I shall go to part D. Part D says, explain the effect of replacing a dielectric by filling the space between the plates of a charged capacitor with a conductor. So instead of putting the dielectric, you put a conductor. So you come as that when a conductor is placed between the plates of a capacitor, negative charges are conducted to positively charged plate, neutralizing the charge on it, and hence the capacitor becomes discharged. So that is how marks would be awarded. So now I shall go to part E. Part E Roman 1 says, what is meant by relative permittivity of an insulating material? So you can simply say that relative permittivity of an insulating material is the ratio of permittivity of the material to permittivity of free space. Alternatively, we can say that this is the ratio of capacitance of a capacitor when the space between its plates is filled with a material to capacitance of the same capacitor. This is why the same must be seen. When the space between its plates is a vacuum. So any of the two is okay, but it's not divisible. Use this one, which is a little brief. And that is how marks would be awarded. So now shall go to part E Roman 2. Part A Roman 2 says, describe how the relative permittivity of an insulating material is determined using a ballistic galvanometer. So we shall also need the circuit diagram. Let's first draw the circuit diagram to ease the description. So you come as that a capacitor C with air between its plates is connected in the circuit as shown. So that's the capacitor C. Switch K is connected to position 1, and after a short time it is connected to position 2. So if I close the switch K to position 1, that means that this capacitor will be charging. Then after you connect it to position 2, where the capacitor will be discharging through the ballistic galvanometer. The first deflection θ1 of the ballistic galvanometer is noted. The test insulator is then placed between the plates of the capacitor and the procedure is repeated. The first deflection θd of the ballistic galvanometer is noted. Relative permittivity of the test insulator epsilon r is obtained from the formula that epsilon r is equal to θd over θ1. And that is how marks would be awarded. So that brings us to the end of this video. Thank you for watching, and be reminded that the next video will be on U.A.C.E Physics 1 of Uneb 2019. So if you haven't yet subscribed, please click on the subscribe button below this video so that you can receive updates when the next video for Uneb 2019 has been uploaded. And also, if you know of any student who is not yet on this platform, please share the link of this video with them via social media platforms like Facebook and WhatsApp so that you can all benefit as a family.